Hey everyone, this is Mr. Couple. Last time we learned how to solve vector problems graphically. Today we're going to learn how to solve them algebraically. The most used vector math skill in IB physics is finding the components of a vector along a set of axes. This is called resolving a vector, and we'll use it throughout the IB physics curriculum. Projectile motion, force, momentum, and field strength. For this reason, you're going to want to keep this video and this paper that we're going to be working on somewhere safe, maybe like bookmarked or filed away somewhere where you can reference it over the next 2 years. So let's look at question 1. Suppose that we use perpendicular axes x and y, and we draw vectors on this xy plane. We take the origin of the axes as the starting point of the vector. So other vectors whose beginning points are not at the origin can just be shifted parallel to themselves until they too begin at the origin. For these questions, we have this vector A, and what we want to do is we want to label the x and y components of this vector. So let's go ahead and label this as vector A. Next, we're going to indicate the x and y components of vector A. Basically, we want to know how much does this vector point in the x direction, and by how much does this vector point in the y direction. And the way you do that is by following these rules here. So from the tip of the vector, draw lines parallel to the axes. So I think the easiest thing to do is actually just draw a line that's already parallel to the axis like this. And then I'm going to grab that line and just drag it over. So click the select tool, and I'm just going to drag this over so that it's at the tip of vector A. And so now what we can do is we can mark the point on the axis where the lines intersect. So that means that this point right here, bloop, and then we can delete our line like that. And then we can draw a new vector that points this way to that point. And so this vector here, that's AX. That's vector AX. So that's going to be vector A subscript X. Remember hitting shift minus or the underscore key to put the subscript on that vector there. So that's AX. And then we can do the same thing to find AY. So we'll use, again, the drawing tool to make a guide of the x-axis, to make an x-axis guide. And then we'll click on the select tool and we'll drag that vector up right along there. We will then grab the drawing tool, mark that point where it crosses the axis. Looks like I just barely missed it. We'll delete our marking, our guide, and then put in, you know what, I should probably use a different color. So I'm gonna use green. And then we'll draw from the origin up to that point, and that's the vertical component of this vector. So this is A subscript Y. So this is the first step of algebraically solving vector problems, and you'll see why in just a little bit. So what I want you guys to do now is I want you to go and draw the vector components for each of these other two here. So pause this video and go do that. So here I've drawn the x and y components of each of these vectors. In each case, vector A points in a different direction, and so that means that the x and y components will also point in different directions. Part B, the direction theta of a vector is measured by referencing the positive x-axis, which is to the east. When theta exceeds 90 degrees, it is often more convenient to reference whichever x-axis gives the smallest angle. This direction is called phi. What we're going to do now is we're going to label theta and phi for each of these drawings. Let's do this with blue, and we're going to do the best we can to indicate these directions. So first we have theta right here. So it's from the x-axis. So that's theta. I'll go ahead and hit the equation tool and draw theta, which is slash theta spacebar. So there's theta. And I'll go ahead and I'll just move this in here to label my angle theta. And I'll do the same thing on the next one. So theta starts at 0 and goes to the vector. So there's our angle theta once again. I'll go ahead and do the same thing again, slash theta. Now referencing phi, to reference phi, you need to go to the whatever x-axis is nearest to the vector. And so you'll notice in this first case, phi and theta are the same. So I'm just gonna make a little statement down here that says phi, so phi, is equal to theta. And so I'm not going to actually draw phi because it's already there. Phi and theta are the same thing. But for the second one, I can actually draw phi because the closer x-axis is this negative side of the x-axis, which will give us a smaller angle. So I can draw phi by going from here to there. and that's my angle phi. I will go ahead and label that right here. So I want you guys to once again pause the video and go label theta and phi for these other two vectors. Here's what your diagram should look like. So let's just check to make sure you got them. So here theta starts at the x-axis and goes all the way around to here, whereas phi is just this negative x-axis angle. And for the last one, theta goes way around here, and then phi is just this angle here. So what you'll notice is that phi is almost always less than theta. And so when you have these weird situations where theta is extending across 90, like more than 90 degrees, it often makes sense to use this angle phi instead. What I want to do now is just really quickly make some mathematical relationships between phi and theta just for fun. There's really no reason to do this. So I'm going to go ahead and move this down here. So in this case, we had, let's flip it around. So let's say that theta is equal to phi. Whoops. Theta is equal to phi. And then we'll do the same thing for the other ones. So let's go ahead over here. So what would theta be in this case? So in this case, theta. So what would theta be in this case? In this case, theta would be, let's see, theta plus phi would give us 180 degrees. So we can think if we take theta and phi and add them up, we get 180 degrees. Over here, let's see what could happen. Well, in this case, if we took theta and we subtracted phi, then you'd get 180 degrees. So theta minus phi would give us 180 degrees. And in the last case here, if we took theta and we added phi, we would have 360 degrees. And there's really no like use to these equations, but it's just kind of, I want you guys to start getting used to just seeing how theta and phi are related in the different quadrants. So if you're in quadrant 1, then theta and phi are the same thing. If you're in quadrant 2, then theta and phi will add up to 180. If your vector is in the third quadrant, then you'll subtract phi from theta to get back to 180. And if your vector is in the fourth quadrant, theta and phi will add up to be 360. Question 2, vector A is shown in the figure to the right. Draw and label the x and y components of A and indicate the angle theta. All right, so let's go ahead and draw the x component of A. So instead of doing the guides thing, when you get good at this, what you can realize is you can just draw this vector and just make sure that it points as far in the x direction as A does. And so one way to do that is just point along A and just try to go down, straight down, and then you'll be pointing along the x-axis as far as this vector points horizontally. And then that's our vector A subscript x. So that's the x component of our vector. I'll go ahead and line it up right along there. And we'll do the same thing for the y component. So starting at this point, I'm going to point as high up as A goes, which is about, you can just try to eyeball it. So I want to go as vertically as that vector goes. Yep, there we go. And then that's our AY. So what I'm going to do now is just go up here and select annotations. I'm going to select my vector A right here, my AY, and I'm just going to copy it and then paste it, and I'm going to move it over here. And so what you'll notice is that vectors AY, the blue one, and AX, they actually form a right triangle. I'm going to go ahead and indicate that right triangle right here, that they actually are forming a right triangle. And don't forget that this angle right here, just like up above, that's the angle theta. So I'm going to go ahead and label that as theta. I'm going to do it in green. So this is theta. We've got a right triangle. We've got these vectors over here, AY and AX, and we've got this right triangle. And so what we can do now is in terms of A and theta, we can say what AY and AX are. So that's what it says here. Use this fact to determine formulas for AX and AY in terms of A theta. Okay, so what we're going to do first is we're going to say, all right, what is AX? So if all that I knew was the magnitude and direction of this vector, then how could I find AX? Well, the first thing you might think is that we might want to try to use the Pythagorean theorem. So if I said that A subscript X squared plus A subscript Y squared is equal to A squared. And that's just the Pythagorean theorem. But the thing is, if you wanted to solve this for AX, You'd also need to know AY and A, but we don't know AY. See, the only given information we have here is the magnitude of vector A and the direction of vector A. And from that information, we want to calculate algebraically the magnitude of AX and the magnitude of AY. We want to find out how many units does this vector A point horizontally and how many units does it point vertically. And if we try to use the Pythagorean theorem to do that, we can't, because the only thing we know is the magnitude of vector A. And so if you're trying to solve for AX, you wouldn't know what AY is. And so you can't actually solve this equation. There's too many variables. So we can't actually use Pythagorean theorem. I'm going to draw an X through it. And then I'm just going to write a little note here that says, can't use too many unknowns. And so we're going to have to come up with a different way of calculating these magnitudes, a different way of algebraically figuring out these magnitudes. And that different way ends up being trigonometry. And so what we can do is we can write out expressions for sine and cosine of this angle. So check this out. So if I say the sine, I'll do this in red. So what I'm going to do first is I'm going to say the sine. So I'm going to do /sine theta. So what's the sine of theta? Well, if you remember, the trick is to remember so ka toa. So I'll write this up here. So ka toa. That's the trick to remember it. And so sine is the opposite over the hypotenuse. So from theta, the opposite is AY and the hypotenuse is A. So sine theta is going to be AY over A. And if we look at this and think about what's known and what's unknown, you'll notice that theta is known and A is known. So we can uniquely determine the magnitude of AY from the sine of this angle. And in fact, if we solve this for AY, what we need to do is we need to multiply both sides of this equation. We need to multiply both sides by A. I'll go ahead and do that in blue. So if I multiply by A on this side, and I also multiply by A on the other side, then what will happen? Well, the A's on the right-hand side will cancel out. And we'll just get what AY is. So let's go ahead and write that out. So that means that A subscript Y, I want to do this in a different color. Let's try this in green. So change to green. Okay, so what we'll get is that A subscript Y is equal to A sine theta. So if we're using just this traditional theta notation, then the vertical component of vector A is just the vector A magnitude times the sine of the angle. Let's do the exact same thing, but using cosine. So equation, I'll do it in red. I'll come right here. So I'll say cosine of theta is equal to, well, cosine is the adjacent over the hypotenuse. So if we take the cosine of this angle, the adjacent to that angle is the x component, and the hypotenuse is A. So we're going to have AX over A. And now we can see the same thing happens again, just like over here, where we knew theta and A, we know theta and A, and now we can find AX. And all we have to do is just multiply both sides times A. So I'll go ahead and do that. So put my little multiply here. Multiplying both sides by A. You know what? I just noticed that it's not really lined up. So I'm going to go ahead and move this. I want this to be lined up with this guy. So I'm going to move them so that they're more or less lined up with each other. All right, so blue, so dot, blue dot here, and I'm going to use the equation, another blue, and I'm going to multiply A on both sides. If we do this, then the A's on the right-hand side will cancel out, so we've effectively moved A to the other side, and we get what AX is. So I can, in green, write this down here, that A subscript X, so the X component of vector A is just A times the cosine of the angle between them. And so these are two extremely useful results. I'm actually going to box these. So where's my box shape using green? I'm going to go ahead and box both of these because they're two extremely important results. In fact, these are in the IB Physics data booklet. They're so important. So just remember what this means. If you want to find the Y component, you can just take the vector A and multiply it by the sine of the angle. And if you want to find the X component, you can just take the magnitude of vector A and multiply by the cosine of the angle. So remember this because it's what we're going to do to start calculating algebraically to find answers to vectors. So let's look at this problem on the back. The figure shows vector A and B. The magnitude of A is 12 units and that of B is 24 units. So vector A is 12 units. I'll just go ahead and put like 12U right here. I'm still in box mode. So I'll just go ahead and put 12 units right here just to remind ourselves that that's 12 units. And then over here, this is 24 units. All right, so what we're going to do is we're going to try to use the formulas that we derived, use these formulas to determine the following: the horizontal component of A and the horizontal component of B, the vertical component of A and the vertical component of B. All right, so let's go ahead and do that. So what I'll do is I'll calculate the horizontal of A and the vertical of A, and then I'll pause the video and have you calculate the horizontal of B and the vertical of B. All right, let's do this. So first up, what I'm going to do is actually draw all these vectors. So I'm going to go up here and I'm going to draw the horizontal component of A. So the horizontal component of A goes this way to about here. And that's the horizontal component of vector A. So I'm going to write that as A subscript X. And I'm going to do the same thing with the Y component. I'm going to label that with blue. And I'll go from the end here, this point, straight down to A like that. So you know that you've drawn your vector components correctly if drawing from A X and AY gets you back to A, and that they're perpendicular to each other. So this is A subscript Y. Okay, so what I seek now is I seek how many units is AX and how many units is AY. Given that the original vector A was 12 units, what will these be? Well, we know that a little bit about right triangles is that the sides of a right triangle are always less than the hypotenuse of the triangle. So we should expect to find answers that are less than 12. So if we come down here and we write an equation, so we're going to start with the red, and I'll say that A sub X is equal to A. Now this is the X component. So I'm going to come up here and I'm going to use the cosine of theta. So I'm going to say cosine of theta. And so now here's where it can get kind of tricky, because where's theta? Well, remember that theta actually goes from the positive x-axis. So theta would actually be all the way around here. So this would actually be the theta to there. So it's not just 45. Theta is actually this 180 up here plus 45. So I have to add that in there. This is where theta actually is. And so down here, when I go to substitute in the values, I'm not going to plug in 45. I'm going to plug in 180 plus 45 because 45 was just phi. So here we go. So I'm going to come back down here and now I'm going to do AX is equal to, okay, so we know what A is. So A is 12 units. And then we're going to do times the cosine of theta, which is 180 plus 45. And I mean, I probably should have put degrees here just to be 100% clear that I'm taking that. All right, so now I can finally use the calculator that I've had sitting over here this whole video. So here we go, turn on the calculator. So I'm going to take 12 times the cosine, and I'm going to open parentheses. I'm going to do 180 plus 45. And now remember, I'm expecting a number that's less than 12. And I got 4.4. So that seems pretty good. You know what I just remembered? I didn't check to make sure I'm in degrees, and I'm not. See, I messed up. I need to be in degrees. So flip that to degrees and then exit out. And I'm going to repeat the same exact thing I just put in. Do it again. And oh, look, this makes way more sense. Negative 8.4. That makes so much more sense because look at which way AX is pointing. It's pointing to the left. So you always need to check that your calculator is in degrees and not radians, because a lot of times if you're not in radians, if you're not in degrees and you're in radians, you're going to get the wrong answer. So make sure you guys always check that. So now I can come down here and finish off this problem. I can say that AX is equal to negative 8 point. Now let's see, looks like we have 3 sig figs in this question. So 1, 2, 3. Yep, 1, 2, 3. So that means we need to have 3 here. So it'd be 8.4. You know what? Let's just write it out to lots of sig figs. 8.485. And then I'm going to use the approximate symbol. Whoops, that's not the approximate symbol. I'm going to use the approximate and then put it to the correct sig fig. So it's 8.49. And what were this is the unit is units because we don't know. It's just some arbitrary vector. So I'm going to come here to a text box and I'm just going to put a U after it for units. Okay, cool. So now we're going to do the vertical component of A. Once again, we should be expecting a number that's less than 12. Look which way it's pointing. It's pointing down. So we should also expect a negative number. Blue. Okay, here we go. So we're going to have A subscript Y. It's going to be equal to A. And now since this is the Y component, we're going to use the sine. So sine of theta. I'm just going to move this up, give myself a little bit more space. And then I'm going to draw the next line. So that means that AY is going to be equal to 12 times the sine of, okay, here we go. Oh, it's the same angle, right? It's the same theta. So it's 180 degrees plus 45 degrees. Okay, we're going to go ahead and throw that in the calculator once again. I mean, we can get fancy here. We can just hit second enter, and we'll put this back in here, and we can just move over to where it says cosine and just swap that over to a sine. And then we get this answer. What? We got the same answer? Well, yeah, of course we did. Think about why that answer is the same for the x and the y components. So negative 8.49, and then come text box to put the unit of u. Okay, did you guys figure out why they're the same? It's because it's a 45-degree angle. When you have a 45-degree angle, that's going to be the diagonal of a square, which means ax and ay have to be the same. All right, I want you guys to pause the video now and go ahead and find the horizontal and vertical components of this other vector over here, of vector b. So pause the video and go do that. Here's what you should have got for the answers to the horizontal and vertical components of b. So one thing that you'll notice is the angle theta. What I did is I did 360 minus 30. And so I just thought if I went all the way around the circle to here, that's 360. And then I just subtract 30. That's totally okay. You could have also, if you would have preferred, you could have also put negative 30 in there and it would have given you the same result. So check this out. So if I just took 24 times the cosine of negative 30, you'll get the same exact answer. You'll get 20.8. And so you could either, in this space right here, you could either put 360 minus 30, which is 330 degrees, or you could have put negative 30, and they are both equivalent to each other. And yeah, the important thing to notice is that the x component is positive. The x component is positive, pointing to the right like this. Looks like I forgot to draw my x and y's, but it didn't matter. So this is the x component of b pointing in the positive direction, and the y component of b pointing in the negative direction. So that's the most common mistake that I usually see, is that students forget to put the negative. That notice that this by is actually pointing downward, so that's why there's a negative sign there. And then the bx is actually pointing to the right, and so that's why this is positive. Okay, what you should have found to be kind of tricky there is it's a little bit hard to figure out these angles. That was a little bit tricky. And so in fact, there's an easier way to do it, and it's to use the phi instead, but something kind of weird happened. So what I want you guys to do is I want you to do this again, but this time I want you to use phi instead of theta, and I want you to see what happens is if you, instead of putting theta in here, if you just straight up put the phi and see what happens. So go ahead and pause the video and do that. Here are the solutions to when you just use phi. So I'm just plugging in 45 for both of these, and I'm plugging in 30 for both of these, just using the phi, the 45, and the 30. And so what you'll notice is that you get the exact same magnitudes: 8.49 for the AX, 8.49 for the AY, 20.8 for the BX, and 12 for the BY. But what you'll notice is that the signs are missing. The positives and negatives are missing. And so you'll see that for this first one here, for AX, we didn't get that it was pointing in the negative direction, but we got the 8.49. And I think you guys will agree that it's a lot easier to just put the 45 in than to try to figure out 180 plus 45. It's a lot easier to just go 45. But if you just go 45, then notice what happens is you end up missing that negative. But just look at the picture. AX is very clearly pointing to the left. And so you can just go back and just realize that that needs to be a negative. And so you could just bloop, stick your negative on there. And then the same thing over here. So if you look at BX is positive. That's why you got the same answer here, because BX was already pointing in the positive direction, but BY needs to be negative. So we're going to need to add that negative on to the BY. And for AY, it's also negative. So you need to add that negative on. So I want you guys to just briefly comment on using theta versus phi to resolve a vector. So if you use theta, your calculator will do all the work for you. It will tell you if it's positive or tell you if it's negative. But it's going to be a lot harder to figure out what that angle is. On the other hand, if you use phi, it's much, much, much easier to plug that into your calculator. It's much easier to just figure out what that angle is. But then you have to do some mental work of actually looking at the picture and cognitively recognizing which way it points and then manually adding those signs on to your answer. All right, guys, so just take a moment and summarize that. I'll see you back in class for the next synchronous session. Bye.